that.
Looks good.
All right, great. So yeah, I'm Chris Havlin. I'm a research scientist at the University of Illinois. And I've been doing some work kind of on the side for fun with visualizing aspect output using YT. And we'll before I go farther, if you actually want to take a look at the presentation at any point, you can go to bit.ly/aspectd and you'll pull up this presentation and you can click through at your own speed and click on some of the links. But so in this brief talk, I'm going to give you a brief overview of what YT is, why it might be useful for folks using Aspect, and then show you the initial work I've done and have some general ending thoughts about future plans for this work. So what is YT? YT is a Python-based package platform for general visualization and analysis. It has some Python optimization on the back end to speed up some of the processes, so it's not pure Python. But from the user perspective, it is pure Python, and it was originally developed for astrophysical simulations, and so it has a lot of adaptive mesh rendering capabilities. So for both visualization, like slicing or volume rendering or analysis of data within your data set. It's parallelized with MPI, can do some serial chunk access when you're working on a single processor, so you can work with data sets that don't fit into the memory of your machine. And then it's also units aware, so it keeps track of the units of the different arrays that get read in as you work with them. And so just as a sample of the sorts of visualizations you can get, on the left here are two volume renderings. The far left is from one of the astrophysical simulations that YT was originally built for. And then the second from the left is a volume rendering of displacement fields that came out of a SpecFim simulation. And I believe they are, I don't remember if they're surface wave or body wave displacements. So those are the sorts of pretty journal cover images that you can create with YT, but in practical use, most people are creating slices. Like this is a slice of through a simulated thunderstorm. The axis here is reflectivity, so it's the actual cloud reflectivity through a thunderstorm. Or these are, in YT jargon, phase plots. So they're 2D histograms where you bin a variable and process that variable within each bin, and I'll touch on that in a bit. So to give you, in case you don't work with Python, just to give you a sense of how you actually work with YT. So this can be either in a script that you store in a Python file or in an interactive Jupyter Notebook environment. But the basic steps to using YT after you install it, or you import that YT package, you load up a data set, you do some operation that defines the extent of the data you want to work with. So in this case, it's pulling out all of the data within that data set. But you can define a number of different geometric extents. So you can pull out sub-regions that are boxes. You can pull out spherically defined regions or elliptical. And then once you define that geometric extent, you can do operations on that geometric extent. So in this case, it's just pulling out a single field from that data set into an array. And the array you get out is a unit array, which is similar to a NumPy array, which is similar to any array in most other languages. And so the unit array, though, is a typical array, but with a units field attached, which is kind of nice. You can catch a lot of errors using this. And then as a slightly more complex example, so in this case, the geometric selection is a slice at a fixed depth of 200 kilometers in this data set that I've loaded up. And then we're going to do one of these phase plots. So you choose a couple of variables, the X and Y, and then you choose the third variable that you want to bin within those, and then some plot setups that I'll skip. And then you get out an image like this. So this is actually from one of the IRIS Earth Model Collaboration NetCDF files up on IRIS from Dubai et al. So this is a plot of shear wave velocity, log of a quality factor, and then the variable that we're binning here is the melt percent. And so one of the neat things about YT is it makes it really easy to sub-select the region that you're working with. So this is just for 200 kilometers depth within this model. So you can easily just change the slice you're looking at and get out a new plot. And so YT has quite a lot of stuff in it that I don't have time to go through. You can check out all the cookbook examples on this page here. It's divided into simple plots, and then some pulling out data set information, doing some statistical calculations and analysis. And so there's a lot in YT, and I think having a workflow in Python allows you to have your analysis coupled to your visualization really closely, which is just a nice way to work, I think. And so I've been playing around with doing that with aspect data. And so before I touch on that, it's worth understanding a bit about how YT is structured. So in general, most visualization software is I would say formulated in this way, where, so in the example of pair review, for instance, pair review is a piece of software that generally reads a set data format, so like VTU files in the case of when aspect is outputting VTU files. And so whatever code you're working with, code X, Y, Z, within that code, there has to be some sort of resampling interpolation routine that takes the solution on your solver's grid for your particular code and interpolates it to the expected format that pair review can then read in. And so the actual visualization software doesn't actually care anything about the code that's generating the solutions that you're looking at. It just cares that the data is in the correct format for it to read. And that's how most visualization software works, primarily because it's easier from the developer standpoint to mandate that anyone using it gets the data into the format that you can read. So YT is a little bit different. And so YT has this concept of front ends. And so what YT does is, so for a given code X, there's some data on the actual grid that you're doing the solutions on. And YT allows you to output that solution to a file format that's a file structure, data structure that is native to your code. And then within YT itself, there are routines that for that code will read in that specific code's data structure and massage it into the form that YT needs to use all of the methods that are implemented in YT. And so there are some advantages to this approach. The primary thing is that you can do direct sampling, visualization, analysis of the solution that's coming right out of whatever grid you're solving on, or particles, which I'll touch on later. But and then the second main advantage is that you can optimize really specifically to the code that and the data structure that you have. So in terms of parallelizing that the input output routines, you really have fine control over how that happens for each of these front ends. The downside is that it does require some initial development from within YT. And so the way that generally works is, so within YT, there are these general Python classes for different mesh and model types, mostly focused on AMR, octree grids, and particle data sets that come out of the astrophysical codes. More recently, though, there was support added for unstructured grids. And so in order to create a new front end, basically you have to write a bit of code in YT that ties all the input output to these abstract classes. And so that's what I've been playing around with aspect. And so from an aspect point of view, we have some options. So YT does have generic data loaders where once you read your data into memory in Python, you can put it into arrays and give it to these generic loaders. This isn't great because you have to read everything into memory, works for small data sets, not for large data sets, doesn't scale well. And in the case of VTU files, for example, the data is stored in binary, so you also have to decode that binary, which for your average user is kind of a headache. There's a second option here, which is the one I'm actually working on these days, is adding an aspect YT front end for the standard VTU HDF output, because there is already in YT, there is another front end that reads in unstructured grids. And so I've been basing the new aspect YT front end off of that. And then longer term, though, there's the possibility of using YT for direct visualization of the AMR output. But that actually would require some development on the aspect side as well to determine like what the natural data structure output is. So yeah. So in terms of this more attainable short-term goal, couple of resources. So at AGU, I presented an initial new front end with some examples how to load in some data and how to do that. I rewrote that last week because of some upstream issues with one of the packages I was using. So I've simplified it a bit. And so if you actually want to click through and look at the notebooks, I recommend starting with the second one. And I will quickly give you the 2-minute preview of this. So I've been working with John a bit on this. He sent me some sample data from some of his 3D continental extension simulations. And so to load up this data, this is a Jupyter notebook. Let me actually make this bigger for you. You can just do import YT, load up the data set, loads in, you get some information about the data set. You can check out some of that information, like the total width in kilometers of the box. You can check out all the fields that get automatically loaded from the data set. And then slicing is as simple as calling YT slice plots, the data set, the plane that you want to slice against, so the normal to the slice, and then the field you want to slice. And so we get out our strain rate field normal to the x direction. And so we see in John's models, he seeds an initial weak zone in the interior of the model where the faults form most. Yeah, and then we can slice it in the opposite direction, so at a fixed depth. And this is setting the center of the slice to be up in this crustal region where the weak zone is, so that we can check out the details of our faults within this weak zone. And you can also do some things like zooming in more by setting the width of the plot, adding mesh lines so that you can actually see the grid that we're plotting here. And this generally works pretty well so far. Of the data sets I've tested, it hasn't hit anything yet that it can't handle, because the VTU format is pretty standardized. And then in this notebook, I did add a bit of an example showing how you might use it to do some geometric sampling. So one of the YT functions, this ds.ray, will pull out all of the values along a line given a start and an end point. So once you define that geometric object, you can pull out any of the variables along that geometric object. And so this is pulling out all of the unstructured grid elements, the strain rate values for all of the vertices of those grid elements along that line, and then doing some manual plotting in that shows the strain rate versus path distance, so you can actually see some of the fault structure in 1D across the model. Yeah, so that's kind of where things are at in terms of usability. There are a couple of short-term improvements I'm working on as I have time. This is kind of just a fun side project, so I'm not sure how quickly these improvements will happen, but a couple of YT improvements are in the works. So the way YT handles unstructured grids is not as efficient as it could be. So there's some improvement to the parallel serial chunk access that I'm working on. And there's some functionality that doesn't work yet with unstructured grids that I'm going to try to add. And then the other big things are adding time stepping support so that you can, instead of loading a single time step, load a whole data set and easily step through time, which YT already has for other data sets. It's just a matter of tying it into the proper classes in the Python. And then I would also like to add kind of an expanded Jupyter notebook series that is maybe for a wider range of audiences. I recognize that these initial notebooks assume you already know Python, so it might be helpful to the aspect community if this is something they're interested in, to have a series of notebooks where it starts at a bit of a lower level in terms of starting to use Python. And then in the longer term, there's some work to do with higher order elements for the VTU. Right now, YT can load in those higher order elements if they're there, but they won't actually use them. They'll just use the corresponding linear vertices of those elements. I think it would be interesting to develop some analysis modules in Python that document standardized workflows for different problems. If you have certain things you want to plot, certain analyses you do, it would be interesting to develop some modules to record those with Python. Open to suggestions. If you have anything you want, send me an email, send me your data set. We can try to load it, see what happens. And then longer term though, I know that the YT group has talked with some of the Aspect Core developers about this, but just to keep that conversation going, it's certainly worth considering trying to do some direct AMR rendering of Aspect data with YT. It's definitely a bigger project, but could be pretty useful, I think. So yeah, I will leave it at that, and feel free to check out the presentation, send me an email. Happy to chat.
Awesome. Thank you, Chris. Because we're behind time, we'll move on and leave questions for the discussion. I posted the link to the presentation in the chat in case anyone wants to see any of the pictures again. Thanks for the work. It looks like a really cool way to visualize our data.